Every time an aircraft weighing hundreds of tons touches down on the runway at speeds exceeding 155 miles per hour, nearly all of that enormous impact force is concentrated onto a single system, the aircraft landing gear. Behind that extraordinary load-bearing capability lies one of the most precise and demanding mechanical manufacturing processes. In modern aviation, everything begins with 3D models, accurate down to the micrometer, followed by massive steel blocks weighing thousands of pounds. These are drilled and machined by industrial CNC systems, heated, chemically treated, and continuously tested for days, all to ensure the system can survive tens of thousands of landings performed by commercial aircraft. Today, we take you inside the aircraft landing gear manufacturing process, the system silently carrying the survival of every flight the moment it touches the ground. The aircraft landing gear manufacturing industry is one of the most closed and difficult to access sectors in aerospace, with a global value exceeding $13 billion annually. Although the world has hundreds of airlines and dozens of aircraft-producing nations, only a very small number of corporations, primarily in the United States, France, and the United Kingdom, possess the core technology required to manufacture this critical load-bearing system. For decades, landing gear has become a symbol of the technological gap between aerospace superpowers and the rest of the world. The reason lies in its extreme complexity. A landing gear set for a wide-body aircraft can weigh more than 30 tons and is made up of thousands of mechanical, hydraulic, and ultra-high-strength alloy components. Even more astonishing, these systems must operate with near-perfect precision under some of the most extreme conditions in engineering.
But even more astonishing is the fact that these systems must operate with precision for decades, enduring millions of impact cycles with virtually zero tolerance for failure. That is why behind every safe landing stands not only mechanical engineering, but also the pinnacle of metallurgy, precision manufacturing, and national technological power. Before any block of steel is cut inside a factory, the entire landing gear system has already been created in a digital environment. Inside aerospace design centers, engineers use CAD systems to build 3D models of every component, from the main strut and shock absorber piston to the wheel assembly and braking system. A landing gear set for a wide-body aircraft alone can contain thousands of different mechanical parts, and many assembly points allow tolerances smaller than the thickness of a human hair. For massive aircraft such as the Airbus A380, the landing gear must withstand loads reaching hundreds of thousands of pounds during every landing. Because of that, if even a single component fails to meet requirements, the entire design must be revised before moving into actual production. To create a system capable of supporting hundreds of tons of aircraft during landings at speeds exceeding 150 miles per hour, the landing gear manufacturing journey begins with massive aerospace steel blocks. Inside heavy industrial machining facilities, high-strength steel blanks weighing thousands of pounds are secured onto industrial CNC lathes, stretching dozens of feet in length. Once the system starts operating, ultra-hard carbide cutting tools begin cutting deeply into the metal surface, removing thick layers of steel to shape the main strut and landing gear cylinder. These carbide tools are made from ultra-hard carbide alloys, materials capable of withstanding extreme heat and wear while continuously cutting high-strength aerospace steel. During machining, friction generates enormous heat, so water and cooling oil are continuously sprayed onto the machining area to stabilize temperature and prevent metal deformation. After the external shaping process is completed, deep hole drilling machines continue drilling through the main strut using carbide drill bits. This process requires extremely high precision because even a deviation of only a few thousandths of an inch can prevent the entire landing gear from supporting its intended load. Technical holes are then reamed to install axles, pistons, and hydraulic connections. For aerospace components, the allowable tolerance can be smaller than the thickness of a sheet of paper. A landing gear system can withstand tens of thousands of landings over several decades, but sometimes a tiny crack that is nearly invisible can be enough to cause the entire system to fail when an aircraft touches the runway. For that reason, after machining is completed, every landing gear component enters an extremely strict inspection stage. Digital measuring systems begin checking straightness, concentricity, and the positions of assembly holes with tolerances measured in thousandths of an inch. Technicians then magnetize the entire component and shine ultraviolet light onto the metal surface to detect microscopic cracks that cannot be seen by the naked eye. Once the UV light is turned on, hidden defects inside the steel surface become visible almost immediately. Components that fail inspection are either rejected or sent back for repair before production continues. After going through a series of highly precise machining and drilling operations, the landing gear components enter the surface protection stage, a process that determines the service life of the entire system under the harsh operating conditions of the aerospace industry. The components are first sent into a shot peening system where millions of tiny steel beads are continuously blasted at the metal surface to increase resistance to fatigue cracking after tens of thousands of landings. Next, the entire component is immersed in a cadmium plating bath to create a corrosion-resistant layer for aerospace steel. For refurbished landing gear assemblies, the old coating is removed using high-pressure sandblasting before the entire treatment process begins again from the start. After plating, the component continues through a cleaning process using water and compressed air before being placed into a furnace for more than 20 hours to remove any remaining hydrogen trapped inside the metal, a factor that can make steel brittle and more prone to cracking after long periods of operation. Once the metal components have completed surface treatment and corrosion protection, the assembly of the shock absorption system officially begins. This component absorbs most of the impact force each time an aircraft lands at speeds exceeding 150 miles per hour. Some load-bearing components are first immersed in liquid nitrogen at temperatures below -200 degrees Fahrenheit to temporarily shrink them, allowing technicians to press collar rings into position using high-power hydraulic presses. When the temperature returns to normal, the metal expands and locks the joints together with extremely large compressive force. Next, the shock absorber piston is installed into the cylinder along with sealing rings and hydraulic joints. Inside this assembly are hydraulic oil and high-pressure compressed gas, a system designed to absorb enormous impact forces whenever the aircraft touches the runway. After completion, the entire shock absorber assembly undergoes leak testing before moving on to the final landing gear assembly stage. While the landing gear shock absorber system completes assembly, another critical component is simultaneously being manufactured to support the full weight of the aircraft during landing: the aircraft tire. The process begins with synthetic rubber, a material selected because of its exceptional heat resistance, pressure resistance, and wear resistance. Inside aircraft tire manufacturing facilities, rubber is rolled into large sheets using industrial rolling systems, extending dozens of feet in length. These rubber layers are then stacked together with high-strength steel wire and reinforcement materials such as nylon or Kevlar, a fiber known for its extremely high strength while still maintaining the flexibility required during landing. Next, technicians begin creating the tire's load-bearing structure by wrapping and compressing the material layers around massive forming drums. Steel bead wire rings are also installed along the tire edges to help lock the tires securely onto the wheel rim under extremely high pressure. In some modern aircraft tires, internal pressure can exceed 200 pounds per square inch, several times higher than ordinary vehicle tires. After completion, the tire is given an initial shape before moving to the high-temperature vulcanization process. Once the load-bearing structure is completed, the aircraft tire enters the stage that directly determines its durability and survival under landings involving hundreds of tons of force. The unfinished tires are placed into massive heated molds, where extreme temperature and pressure transform dozens of layers of rubber, steel wire, and reinforcing materials into a nearly solid structure. Inside the vulcanization system, the tire is heated at temperatures above 300 degrees Fahrenheit for several continuous hours. Under intense heat and pressure, the material layers begin bonding tightly together, creating enough strength and load-bearing capability to withstand the enormous landing forces of commercial aircraft, weighing more than 1 million pounds. After vulcanization is completed, the entire aircraft tire enters the final inspection stage, the process that determines whether it can withstand landings involving hundreds of tons of force. Technicians first inspect the shape and dimensions of each tire using highly precise digital measuring systems to ensure that the overall structure remains stable after the heating process. Next, the tire is inflated under high pressure to check sealing performance and load retention inside the rubber structure. Some factories also use industrial X-ray systems to detect hidden defects inside the reinforced steel layers and internal material layers of the tire. The tire tread surface then undergoes further inspection to ensure proper runway grip during landing. On average, a commercial aircraft tire can withstand more than 200 takeoffs and landings before replacement or refurbishment becomes necessary. After all assemblies complete processing and inspection, the landing gear enters the final assembly stage, where thousands of individual mechanical components are combined into a system capable of supporting more than 1 million pounds of large commercial aircraft weight during landing. Inside aerospace factories, main strut assemblies weighing thousands of pounds are lifted using industrial overhead cranes and connected with a shock absorption system using high-power hydraulic equipment. Technicians then install wheel axles, stabilizing links, wheel assemblies, and braking systems using large load-bearing bolts. Next, aircraft tires are mounted onto the wheel axles and filled with high-pressure nitrogen gas. In some modern tires, pressure can exceed 200 pounds per square inch to withstand enormous loads during landing. Before being approved for installation on an actual aircraft, the entire landing gear system must go through extreme load tests designed to accurately simulate real operating conditions. Throughout the testing process, high-pressure hydraulic oil is continuously pumped through the entire system to check for leaks at every piston, valve, and oil line. The braking system is also repeatedly activated to verify performance under temperatures exceeding 1,000 degrees Fahrenheit during emergency braking situations. The landing gear then moves into cycle testing, one of the harshest tests in the entire process. Testing equipment continuously raises, lowers, compresses, and vibrates the landing gear assembly for several days or even several weeks to simulate tens of thousands of takeoffs and landings throughout the aircraft's service life. During this test, every piston movement, joint stability level, and pressure inside the hydraulic system is continuously monitored by sensors. Only landing gear systems that pass all load and cycle tests are approved for installation on actual aircraft. From aerospace steel blocks weighing thousands of pounds to tires capable of handling pressures exceeding 200 pounds per square inch, the entire landing gear system is the result of months of manufacturing, load testing, and extreme inspections to ensure that aircraft can touch down safely after every flight. Behind a landing that appears to last only a few seconds are thousands of mechanical components, high-pressure hydraulic systems, and materials engineered to survive hundreds of tons of impact force through tens of thousands of continuous takeoffs and landings. And that is how the aerospace industry creates one of the most complex and important mechanical systems on every modern aircraft. If you found this manufacturing process impressive, do not forget to leave a like, subscribe to the channel, and comment below. What massive manufacturing process would you like the Factor In to explore next?